All right, so we are continuing section 8.3. We were able to do last, let's see here if I can, last week we finished up talking about section 8.2, which was problems involving series. And a series, of course, is when you add up the terms of a sequence and you get an infinite series, and the series will either converge or diverge. If the series converges, the series then has a finite sum. If the series diverges, then the series, well, that's not as interesting, right? We're interested in series that converge. So we need to be able to tell if the series converges or diverges. And you learned last week that there's different kinds of series. You have geometric series, you have harmonic series, you have telescoping series, and you've had experience with all of those kinds of series in your section 7.8.2 homework that was due today. Now, in section 8.3, we continue talking about series, and we look at series that are a little bit unfamiliar to you. They don't fit in the category of a strictly harmonic series or geometric series or telescoping series, but nevertheless, we want to be able to determine whether they converge or diverge. And in our last class, we had done question number A, and we determined that this series converged based on comparing that series to a convergent P series. Now for today, where we're starting off in section 8.3 is the second example. Now the second example here, I actually changed the example. Originally, if you look back in the recording or in your notes, hold on here. Why is okay, hold on. There we go. Originally, the series I had for part B on this problem was this series here. And, you know, I'm thinking about your homework today, your homework on 8.3, that's due Thursday. And I decided to do this example instead. So this problem here, I think you could figure that out. I want to focus on this series here. So take a moment to copy that series down, and then we will discuss whether it converges or diverges. I'll give you a moment here. So we did part A in our last class. Now we're focusing on part B for this question. Okay, so it's what makes this series here, and let me just clear this here. Okay, so this series, notice the series starts at n equals 2 instead of n equals 1, but that's okay, because what determines the convergence or divergence of a series is how the terms of the series behave as you look at terms further into the series. Okay, so what makes this series kind of difficult for us to? I mean, what would you say makes the series a little bit difficult? What part of the series? Yes, Taj, the square root is definitely makes the series a little more, let's say, interesting. And also don't forget we have a +1 there under the square root. So what we're going to do here is notice too, well, I'll just notice that the series, all the terms of the series are positive. Okay, if we were to expand this series out, hold on, I didn't want to touch that. I want to touch this here. If we were to expand the series out, okay, if I wanted to write down just a few terms of the series, you know, n equals 2 is the first value of n, so you'd have 1 over 9, because 9 is 2 cubed plus 1. The next term of the series would be 1 over the square root of what? Square root of 28, because 28 is 3 cubed plus 1. And the series continues, okay? It continues. But all the terms of the series are positive. So in section 8.3, where we have these, we're going to be using the comparison type tests, and then you're going to learn about an integral test. We assume that the series has all positive terms, or eventually all the terms of the series would be positive. So we're going to use the comparison test. Let me show you the solution here for part B. Let me go forward here. We did this one. This is for part A. We've done that last time. Here's part B. We're going to use the comparison test. So let me give you a moment to copy this part down, okay? And then I'll talk about that. Let me just give you a moment here. Okay, so this this 1 over the square root of n cubed plus 1, we'll call that term a sub n. And we know that 1 over the square root of n cubed plus 1 is less than 1 over the square root of n cubed. We'll call that b sub n. Okay, so when you are doing the comparison test, you have to compare your series to another series that you that you know something about. So, well, 1 over the square root of n cubed can be expressed as 1 over n to the 3/2 power. And we recognize the series where n equals 2 to infinity of 1 over n to the 3/2 power. That's a convergent p-series. Again, it doesn't matter what the starting index is for the series, okay? N could start at 100, for instance. We're having it start at n equals 2. That doesn't determine whether you have a convergent p-series. What determines that is the value of p. And in this case, p is 3/2 power. That's greater than 1. So you have a convergent p-series. Well, because of that, by comparison, our series has to converge as well. Okay, our series will also have to converge. So a way to think about that is that you have, like, let me just, maybe I'll write it here. Hold on. All right, you have the series, this series, our series, that you don't know if that series converges or diverges. But that series, the sum would have to be smaller than this p-series. So this p-series has a converges, so its sum is finite, right? The sum is finite. So in this series, the p-series is greater, it's greater than our series of interest. Well, since the larger series has a finite sum, the smaller series would also have to have a finite sum. So that series converges also. So when you have a larger series, again, this is when you have series that have all positive terms. When you have a larger series that converges, and you know that series, well, if you have a series that converges and you know that series is larger than the series you're interested in, then your series has to converge also. That's the idea behind using the comparison test to establish convergence of a series. Okay, does that make sense? Are there any questions? So these convergence tests, you have to be very careful with them, because in your, like, homework for section 8.3, which I'll make available a little later, a lot of the problems in there, they're multiple choice, and they'll give you a series and they'll say to you, does the series converge or diverge? And if and you have like one try to get the answer right. So you have to take your time with these problems, right? These multiple choice problems. All right, well, if you're good with this, let's do a few more. Well, hold on here. Let me just, one moment. I want to bring up something from the ebook. Okay, I'm bringing it up now. Let me get it. Okay, so this is the comparison test that is in the book, and we used part A of the comparison test. We had the larger P series that converged, and so our smaller series converged. Now, for part B of the comparison test, you can show a series diverges if, for instance, if your series is larger than another series and that other series diverges, then your series has to diverge. So that's the two ways that you can utilize the comparison test. Now let's go ahead and look at a few more examples here. One moment here. Okay, take a moment to copy these two examples down. Okay, so these are two very interesting looking series. The first series, what does that series almost resemble? What kind of series does the first series here almost resemble? That's right, Ange. It almost resembles a geometric series. Okay, and so when I think of this series, when I look at this series, I think of this series, which incidentally can be expressed as this series, and this series from n equals 1 to infinity of 1/2 to the nth power, that's a convergent geometric series, right? Because it has a common ratio of 1/2, and 1/2 is smaller than 1. Absolute value of 1/2 is smaller than 1. So if we're going to use a comparison test, it might make sense to try to think about comparing this series to this geometric series. You see what you see? When you make a comparison test, you try to relate your series to a series that you're familiar with. All right, are there any questions on part A before we move forward? We'll see if this strategy works, by the way. All right, let's go ahead to the solution for part A. And it turns out that, well, let me just put this like this. So the series, our series, the term, the a sub n term is 1/2 to the nth power minus 1. And we're going to compare that term to the b sub n term 1 over 2 to the nth power. It turns out that the terms in our series are greater than 1 divided by 2 to the nth power. Okay, so because of that, the fact that the geometric series converges gives no information about the convergence or divergence of the series that we're interested in. It gives no information. Let me give you a moment to copy it down to here, and then I'll show you at the bottom here. I'll try to be a little more, I'm trying to be as intuitive as possible with you. Let me know if you have any questions. All right, so again, the comparison test here isn't going to work. And the reason is because our series, let me just, here's our series right here. Our series is bigger than the convergent geometric series over here, where n equals 1 to infinity of 1 over 2 to the nth power. So what happens is the geometric series has a finite sum, but then our series, which has to have a larger sum, we don't know if that sum is finite or infinite. The sum could be finite or it could be infinity. We don't know. So the comparison test fails in this problem, that type of comparison test. In other words, you can't establish convergence or divergence using the regular comparison test. Are there any questions on what you're seeing here? Please let me know if you have any questions. Who's feeling good so far? Maybe give me a thumbs up if at least intuitively you understand. Okay, Nathaniel is good. Javier says it makes sense so far. Excellent, excellent. Well, the question is, what are we going to do? What are we going to do here? We don't want to get the question wrong. We don't want to get wrong on the fourth exam, a question like this, where you have one chance to get the answer right. We want to be able to correctly identify if the series converges or diverges. Well, we can't ignore the fact that when n is large, our series is going to, because I want to say this the right way. Yeah, for our particular series, okay, let me just write it maybe here as just an aside. I kind of like to have stuff, all together. But when n is large, 1 over 2 to the nth power would be approximately the same as 1 over 2 to the nth power minus 1. So it tells us that for both of these series, if we look well into the series at terms, like for large N, the terms of the series are going to be almost the same. So the behavior of the geometric series would have to be equivalent to the behavior of our series, or I should say the behavior of our series, the eventual behavior, should behave like the convergent geometric series. I mean, intuitively, that should make sense. So what we're going to do is we're going to use another test to help us here, called the limit comparison test. So let me go back to the ebook. And show you this test. This is section 8.3. So the limit comparison test says that suppose you have two series with positive terms. And let's say you take the ratio of the terms of those series, so a sub n over b sub n, and you let n go to infinity. If the limit equals a constant, where c is some finite positive number, then both series will either converge or diverge. If the ratio of the terms of the series equals some constant, you're saying that eventually, I want to be careful, if you're saying that the limit as n goes to infinity of the ratio of the terms of the series is a constant, that means eventually the terms of both series are in proportion to each other. So the behavior of one series will be equivalent to the behavior of the other series. That's what the limit comparison test is. And we can hopefully utilize it for our particular problem. So let's go back here to our problem. Okay, and we learned that the comparison test did not work. Let's talk about the limit comparison test. Okay, so here, since the comparison test did not work, okay, we're going to use then the limit comparison test. So you're going to let a sub n be 1 over 2 to the nth power minus 1, and b sub n will equal 1 over 2 to the nth power. Now, hold on here, class. Let me just, what we do is we look at the ratio of these terms and how does the ratio behave as n goes to infinity. All right, well, this here, this limit, I mean, we want to find the limit. I'll add in a little detail here. And what we can do is multiply the top and the bottom by, the numerator and denominator by 2 to the nth power. And when you do that, the limit of the ratio of the terms will equal the limit as n goes to infinity of 2 to the nth power divided by 2 to the nth power minus 1. Now, what we can do to figure out that limit, it's an indeterminate form. You have a infinity over infinity. So we could use L'Hopital's rule on it to try to get our answer. But we could also then instead of doing L'Hopital's rule, which would involve us needing to find derivatives of the numerator and denominator, we could multiply numerator and denominator by 1 over 2 to the nth power. And when we do that, we'll get then the limit as n goes to infinity of 1 divided by the denominator 1 minus 1 over 2 to the nth power, right? Because, of course, you're distributing. Try to make this look good. One moment. Okay, so what happens then is, well, now that the limit is written as you see here, we know that when we let n go to infinity, this is going to equal 1 over 1 minus 0, because 1 over 2 to the nth power, and as n gets large, that approaches 0. So we get 1, and 1 is greater than 0. So 1 is the C, okay, value. So this is saying that these two series, the terms of the two series, are essentially the same. And so our series has to converge because the other series converges. I have that written out nicely on the next page, but are there any questions on what you're seeing here using the limit comparison test? You notice that you know based on your series what the a-nth term is. The b-nth term, you have to figure out what you're going to use, but usually you use something similar to your a-nth term. Use your intuition. Okay, well, let's finish the problem off then. So this means eventually our two series, the series with n equals 1 to infinity of 1 over 2 to the nth power minus 1, and the geometric series n equals 1 to infinity of 1 over 2 to the nth power. Eventually, those series are very similar. And so the fact that the one series converges means the other series has to converge as well. So it's sort of intuitively, you really, I think intuitively, you understand the limit comparison test, but we're just writing it out more formally. Please let me know if you have any questions. Let's see, Mario says well, you see, you wouldn't have a constant that is negative, because if the constant were negative, that means the terms of one series would be positive and the other series, the terms would be negative. We are comparing in section 8.3, we are looking at series that have positive terms. So limit comparison test, you would not get a negative. You would not use the limit comparison test if if one series had positive terms and the other series had negative terms. By the way, you can also have, I'll mention this, like suppose you had a series like this. Suppose you had a series where you had -1 to the nth power times 1 over 2 to the nth power. This series here is called an alternating series. This is an alternating series because the -1 to the nth power is going to make some of the terms positive, some are negative. If I write out just, you know, the first couple terms of the series, whoops, hold on, I got something crazy. I hit a crazy button again. Hold on. Let me get out of here. Hold on, where am I at here? I went, yeah, okay, there we are. Okay, so you see, no, that's an 8. Okay, so the series, you know, I think you agree that the terms of the series, -1/2, plus a 4th, minus an 1/8, and so forth. So you see the terms of the series alternate between positive and negative. For this kind of problem, without doing some modification to it, you cannot use the comparison test. You can't use the comparison test nor the limit comparison test because, again, the terms of the series are not all positive. So you see, Mario, that would never happen using the limit comparison test for because you would only use it for series that have positive terms. Okay, are you comfortable with that, Mario? Excellent, excellent. Okay, well, let's go back and look at that other series. Hold on, what happened to my stuff here? Hold on. I was sharing files and they've kind of hold on here. Where am I at here? Hold on, everybody. Hold on. Gosh darn it, what's going on here? Hold on. Wait, it's down here. All right. All right, we're good. We're good. All right, let's look at B now. Let's look at B. So you have a series here where they've written out the first 5 terms. 1 plus a third plus a fifth plus a seventh plus a ninth plus and so forth. So what's missing from this series that we've seen in so far? What's missing that we don't have for this particular series here in B? What do we need to have for that series? What would be nice to have? That's right, Taj. It would be great to have a formula for that series. So let me go to the whiteboard here and let's see. Let's get a formula for that series. So one moment here. Okay, so let me write down some terms. Okay, so what do we have here? We have 1 plus a third plus a fifth plus a seventh plus a ninth and so forth. So, you know, this is the first term. Maybe I'll put it above. We have the first term, second term, third term, fourth term, fifth term, and we want the formula for the series. And you're right. The formula for that series is summation n equals 1 to infinity of 1 divided by 2 to the n minus 1. Now, again, let's think a little bit. Let's think here. All right, for large n, 1 divided by 2n minus 1 is approximately equal to what? 1 over, well, how about 1 over 2n? So if we wanted to use the limit comparison test, we could let the a sub n be 2n minus 1, and we'll let b sub n be 1 over 2n. Now I'll finish I have the problem finished out on paper, so I'm going to go back to the slides, but I'm just trying to help you develop a strategy for approaching these problems. Are there any questions so far? Okay. Well, then let's get back to the problem. I mean, we're on the problem, but let me get back to the slide. Okay, so here we are. We're doing part B. And here's the formal solution. So we found the formula for the series. Indeed, we did. And we're going to use the limit comparison test. Going to use the limit comparison test for this one. So indeed, we'll let a sub n be 1 over 2n minus 1, and we'll let b sub n be, well, actually, you know what I'm going to do, class? I'm going to do something a little different. I'm going to let b sub n be 1 over n. Okay? I want to do something a little bit different. I could let b sub n be 1 over 2n, but I'm going to let it be 1 over n. And you'll see why. So let me give you a moment to copy down to here. Okay, so, all right. So I look at the limit as n goes to infinity of the ratio an divided by bn, and I get the ratio there, and what I can do here is, if I want to just add a little extra step here, it's really beautiful stuff. I can multiply by n on the top and the bottom, and that'll get me this limit as n goes to infinity of n divided by 2n minus 1. But that's an indeterminate form. Okay, so I could use L'Hopital on it, but I'm going to just choose to multiply numerator and denominator by 1 over n. Okay, and of course I distribute the 1 over n on the bottom to the two terms. And when I do that, we get the limit as n goes to infinity of 1 divided by 2 minus 1 over n. And that, when we take the limit, that's just going to be 1 over 2 minus 0, and that gets us a half. Okay. Now, why do you think I chose 1 over n here? Why did I pick, instead of 1 divided by 2n, I chose v sub n to be 1 over n? Why would I do that? What do we know about the series where n goes from 1 to infinity in the terms of 1 over n? What kind of series is this? That's right. It's a harmonic series. That's right, Taj. And I believe it was Ange noted that it's a piece series where n equals 1, too. So it has to diverge. It's a divergent piece series. In fact, it's a harmonic series, and that series diverges. Well, the fact that eventually our series, the terms are going to be approximately half the size because the ratio is a half. The terms of our series are going to be approximately half as large as the terms of the harmonic series. But since the harmonic series diverges, our series would have to diverge too, because half of infinity is still infinity, you see. So if I want to say that, I mean, I think I said that nice, but on the next page, I formalized it a little bit more. So our series eventually, notice I say eventually, that means when n is large. Our series eventually will behave like 1/2 times the harmonic series by virtue of the fact that the ratio of the terms in the limit equals a half. So therefore, since the harmonic series diverges, then our series also has to diverge. So it's sort of like you can't, the truth comes out. No matter what the series does in the beginning, it's the eventual behavior of the series that will determine if the series converges or diverges. And our series acts like a harmonic series, just the terms are half as large. But but it acts like it acts like 1/2 times a harmonic series. That's what it acts like. How many find this? I mean, I'm trying to put in some words, some intuitive to give you an intuitive feel. Is this helping these Dr. Duty explanations that I'm kind of discussional here? Is this helpful? Like this page, what you're seeing, how many of you are finding it somewhat helpful to get you comfortable with series? Oh, great. All right, Javier, Anj, Jan, that's great. That's great. Okay, good. All right, I want to look at another example, but let me give you a moment just to copy this down. I want to look at an example from the book too. All right, are there any questions before I move over to the ebook? Okay. Okay, well, let me go over to the ebook here. I want to look at one more example before we go on our break here. Let's see. So another test that you need to be aware of from section 8.3 is a test known as the integral test. And this relates improper integrals to infinite series. How many recall improper integrals from section 5.10? You haven't seen them in a while, but how many remember them? Where one of the limits is infinity. Sure, Taj remembers that. Ange remembers that. So what does the integral test say? It says, suppose you have a function that's continuous, positive, and decreasing, okay, on the interval from 1 to infinity, and let a sub n be the function evaluated at n. Then the corresponding infinite series is convergent if and only if the improper integral is convergent. So, in other words, like in part A there, it's in purple or pink. If the improper integral converges, the series converges. If the improper integral diverges, then the series diverges. So this is known as the integral test. And it's very helpful for establishing convergence or divergence of series that you couldn't easily use a comparison test on. And they note here that the integral test, it's not necessary to start the series or the integral at n equals 1. So like, for instance, if you had, like they show these, if you had the series where n equals 4 to infinity of 1 over n minus 3 cubed, well, you're starting at n equals 4, but that's okay. What determines the convergence or divergence of the series is the eventual behavior of the terms as n gets large. The eventual behavior of the terms of the series as n gets large. So, all right. So let's look at an example here of this. Let's look at an example. We'll look at example 1 here. They mentioned too that the function doesn't always need to be decreasing. It's just eventually it'll be decreasing. That's just, to help you understand. It's the eventual behavior of the series that matters. So, okay, example 1 says determine whether this series, okay, maybe I'll remove the highlight and put it back in. Okay, determine whether the series n equals 1 to infinity of the natural log of n divided by n converges or diverges. Now that series, it would be difficult to use the comparison test on that, or the limit comparison test. It would be difficult. So what we're going to do is we're going to use the integral test. And what they do is they establish here in the solution, they establish that the log of x divided by x is positive and decreasing for x greater than 1. So what they do is they take the derivative of the function. Remember in calculus 1, how do you know if a function's decreasing? You look at its derivative, and where the derivative is negative, the function's decreasing. So they establish that the function will decrease for x greater than the Euler's number e. Okay, so that's fine. For the problems in your homework where the integral test is involved, the functions will have positive terms and be decreasing, or they'll be eventually decreasing. So let's get forth to then using the integral test. Here we go. So here's what we do. We examine the function log of x over x. We look at the improper integral from 1 to infinity of the log of x over x dx. And they now leave out a step. They did a substitution. They let u equal the log of x, and they get the antiderivative there of which is the log of x squared over 2. And they put in the t and the 1, and eventually you get infinity. So the improper integral equals infinity. You've done enough improper integrals. You know how to compute an improper integral, right? So the limit equals infinity, and therefore, since this improper integral diverges, this series also has to diverge by the integral test. Okay, so that's known as the integral test. And they show why it's true in the book, but let's focus right now on, well, I want to give you a little time to practice. So one moment here. Well, first, are there any questions on the integral test? I mean, who's feeling good? Who's feeling reasonably good with what you're learning in section 8.3? Taj, yes. Taj is saying, could we use the integral test to show that the harmonic series diverges? We could. I can show you that real quick. So like if we have, you know, the harmonic, that's actually a great thought there. So you know, here's your harmonic series, and you had a way, they show you proof of that, why that series diverges. They showed you proof in section 8.2. But if you use the integral test, you would look at the integral from 1 to infinity of 1 over x dx. And the antiderivative of 1 over x, what's the antiderivative of 1 over x? Natural log. All right, so that's right, Tosh. So I guess, okay, to be more formal, of course, we have to let t go to infinity, and then replace our infinity on top with t. So now we have the limit of a proper integral, and the antiderivative of 1 over x, as you said, is the log of the absolute value of x, 1 to t. Okay, and so we get the limit as t approaches infinity of the log of the absolute value of t minus the log of the absolute value of 1. But the log, hold on here, I like things to look nice. The log of the absolute value of 1 is 0. And the log function, the log of t, as t goes to infinity, well, that's infinity. Okay. And so, therefore, that's a way to show, we use the integral test to show that the harmonic series diverged. Okay, so how many are, I hope you're feeling good. Thank you, Taj, for that good question there. Are there any questions before I stop the recording? Okay, I'll stop the recording. Very good. And we're going to be talking, now section 8.3, I'll mention one thing. we need to talk now, like when we establish a series converges, okay, if a series converges, we might want to know, well, what is its sum? What is its sum? Because the sum's finite. We can estimate that sum using in section 8.3 what's called the remainder estimate for the integral test, and we'll get into that after break. All right, let me stop the recording here.